do we remember what our exponential graphs look like?
Fast increase.
Yep, fast increase if it's an exponential growth. So if I have y equals, let's say 2 to the x. Okay. What are some values that we might plug in there? 3? Okay. What else? 0? Sure. What else? Okay. What do we also probably need to plug in?
A negative.
Some negative numbers. Okay. So, good review. What happens when we have a negative in our exponent? Yeah, so if I have 2 to the negative second, remember it gets flipped, and then we would have 2 squared gives us 4. So we have 1/4. Which means likewise, if we have a negative 1, we would get a 1/2 there. Okay. And also, one of our exponent rules, if I have something to the 0 power, what is it always going to be? 1. Then 2 to the first is 2. 2 squared gives us 4. 2 cubed gives us 8. And so forth. So, like we said, as we go to the right, we are going to be increasing faster and faster and faster and faster. So it's different than like a linear graph, which increases at a constant rate. Yes. This one increases at an increasing rate, meaning it's getting faster, going up. Now, as we go to the left side, what's going to be happening?
Closer and closer to 0.
Yeah, so it is decreasing, specifically getting closer and closer to 0. What do we have at 0? Yeah, we have a horizontal asymptote there. Do we know why we have a horizontal asymptote there?
Isn't it because like it never will actually reach 0?
Agreed, but why? Is there a number that I could plug in there to my exponent, so like 2 to the x, that I would get out either 0 or a negative number? No, because when we plugged in 0, right, that gave us 1. When we keep plugging in more and more negative numbers, we're just going to get smaller and smaller and smaller fractions, right? So there's not a way for me to just plug in a number there when I just have an x. Like if you started putting in other stuff like x minus 1 or stuff like that, that changes it. But just with like a normal x, there's not. So what is our domain for this graph? Correct. All of our x values are fair game. We are good to plug in any number that we want there. Or in other words, I can go x to negative infinity, I can go x to positive infinity. Now, for our range, do we have any restrictions? Or any y values that we don't end up getting? We don't get 0, and we also don't get negative. So what's our range going to be? We just said we can't get negatives, right? So what? 0 to positive infinity. And remember that since it can't equal 0, we put the parentheses there instead of like the bracket. Okay. Now, also thinking about our horizontal asymptote, if I'm going to the left side of my graph, how do we describe the left side of our graph? Back to our like notation that we talked about when we did in behaviors. So if I'm talking left and right, which variable am I talking about? X. Okay, and if I'm going to the left, what is X doing? decreasing or going towards negative infinity. So, as x goes towards negative infinity, what is y doing, or f of x? Yeah, it's getting closer and closer to 0 there. That's because we have that horizontal asymptote. Now, this is specifically 2 to the x, but we could make this more generalized and just make it b to the x, and it is going to follow that same pattern. Usually we just stick with 3 key points, so -1, 0, and 1. When we plug in 0, we are always going to get 1. When we plug in -1, we're going to get 1 over b, and when we plug in 1, we're going to get b. Now, for this type of graph, my blue graph, this is specifically a growth graph. Do we remember what has to be true in order to get a growth graph? It has to be increasing, yes. And so for our function, that's going to mean that our b value has to be bigger than 1. Do we recall what happens when we have a b value that is in between 1 and 0? So we're actually going to end up with a decay graph. So like this would be like something, if I had 1/2 to the x power, yes? So if I had 1/2, notice that if I plug this in to my right side, right, notice 1 over 2 would actually be what? If I have 1 divided by 1 divided by 2, what does that give us? 2, right? Because I would multiply by the reciprocal. So that means that on the left side is actually going to be where it's getting bigger and bigger. And notice that b, if my base is a fraction, is just going to be that fraction still. So what ends up happening is that it gets closer and closer to 0 on that right side of the graph instead. So now your domain and your range are still the same, but now it is as x goes towards positive infinity, f of x goes towards 0. Again, just kind of describing that behavior for our asymptote. Okay, some examples. Alright, here, what is our base? 3. Okay? So I have x. So to make a table, what were our 3 key values that we want to plug in? -1, 0, and 1. So if we plug in -1, what are we going to end up with? 1/3. Because it flips it using that negative exponent property. If we plug in 0, what do we always get? 1. And then 3 to the first power is indeed going to be 3. So notice, these are my 3 key points. I connect them. Okay. Do I need many other points to know what the rest of my graph is doing? No, what we can do instead is say, okay, if I have a 3 to the x, that's what type of function? An exponential. And we said that on the right side of our graphs, if it's an exponential growth, which since it's 3 is bigger than 1, we know that this is going to have to continue to increase faster and faster and faster. And on the left side of our graph, we said that it's going to have to get closer and closer to 0. So we don't need really a ton of points there, as long as we can remember what the general shape is. And we really just need those 3 key points to kind of graph the middle part. What questions do we have? Okay. This one maybe. Okay. So that's a growth graph. What type of graph are we going to get here? Why?
Because
Which is? It's less than 1. Because technically it could be a fraction, like if I had 5/3, right? That's still a fraction, but it's still a fraction that's bigger than 1. So it would still be a growth graph because 5/3 is bigger than 1. Does that make sense? So just be careful with that. Same thing with decimals. If it was 0.25, right, that would be a decay graph. But if I had 1.25, even though it's a decimal, that's still a growth graph because it's bigger than 1. Okay. So let's look at, just in case we didn't quite see, notice that when we plug in -1, I have 1/3 to the negative first power. Okay? And we said that our negative exponent does what with it? Makes it a fraction. Well, so it's going to put this fraction in the bottom of a fraction, so I would get 1 over 1/3. So we multiply by the reciprocal of 1/3. Well, the reciprocal of 1/3 is just going to be 3. Same thing if I had a -2 here, right? I would still square it and get 1/9, and then my 1/9 is in the bottom, so I get 9, which is why the more negative that we get with these, the farther that we're going to go up. Now my 0 is always 1, no matter what my base is. And then if I have 1, it's just going to be 1/3. And again, since we should know what our general shape is, we really just need those 3 points in order to graph the rest of it. What questions do we have there? Now, those are 2 examples of our parent graphs. Okay. Do we tend to just graph parent graphs? No. What do we usually add in then? What can we do to our graphs once I have a parent graph? Transformations. So remember, we can shift it left, right, up, or down, which is also called a translation. We can stretch or compress it, which is given to us by the number on the outside, or we can reflect it and make it line down. Remember, we've talked about these transformations before. It's just now we're specifically looking at them with our exponential graph. And this time our h's are going to be in our exponent. Our k's will be outside, and then the a's are going to be in the front. So, what is our base here? 5. Can I multiply my -1/2 and my 5 together? Why not? Yeah, but like, why can't I just make it -5/2 to the x minus 2?
Because there's an x in the
In the exponent, yeah. So remember, our order of operations says exponents first. But if I don't know what x is, then I can't do my exponent first, which means I then can't do my multiplication. So like, we can't really do much else with it at that point. So if we just look at our base, so 5 to the x, okay? I'm just again looking at those key points. So we get 1/5, 1 and 5. You don't have to graph the parent graph first, but I think sometimes it helps just to see what the transformations are doing to the graph. So that's my parent graph. Then what's happening on the front of that? What does that negative 1/2 be?
There's 2. Either compresses or stretches it.
Correct? And if it's smaller than 1, that means it's going to... No, that's the negative part. The negative, yes, we'll flip it across my x-axis. But since it's a 1/2, is that going to stretch or compress it? So think of it like slope, right? If I'm stretching it, that means I'm making it taller faster. So it would have a bigger or higher slope. Yes, so it would be greater than 1. If I'm compressing it, that means I'm making it like not grow as fast, or I have a smaller slope. So it will be compressing it. Which values does that 1/2 change? Does it? So it changes the numbers that I am plugging into my x. No, it doesn't change the numbers that I plug into my x. However, it does change the numbers that I'm going to get out on my y values. Yes? No, maybe. Okay, so we are now going to multiply each of these outputs by a negative 1/2. So we get negative 1/10, negative 1/2, and negative 5/2. So it looks something like that. And then what's the last thing that we have to worry about? The -2 that's up in my exponent, yes? What did we say that -2 does? It's going to be horizontal. And remember that when it's horizontal, it's the opposite sign, or opposite direction of the sign. So that's going to move it 2 places to the right. So what's the domain for this graph? My domain did not change, but did our range change? Yeah. Why? Yeah, so now it's going to be all the negative numbers. So instead of starting at 0, it's going to stop at 0. Yes? Alright, I want you to try the next one on your own. There you go. Turn and check with the neighbors, see if you got a similar graph.
So after you found the points, you plot it and then you do the transformations?
I mean, like, technically you could move it from the points on the table. I just think that's kind of hard to, like, visualize what it's going to look like in the left two down from like just the table. That's why I like the graph version. So we want to start by looking at just 1/4 to the x. And then we're going to multiply each of our y values by 2. So my parent function looks something like that. The shape of the graph when it's been multiplied by 2. Oops, sorry, that was backwards. Both those, my fault. Should look like that. There we go. Because it's a decay graph. Then we want to stretch. So 8, 2. So we've stretched it by 2 now. And then our last thing is going to be to move each of those points left 2, down 3. So we should end up with something like that. Now do notice that since we have shifted everything down 3, that also includes our asymptote. So instead of getting closer and closer to 0, we're now getting closer and closer to -3. So our domain is still going to be all real numbers. But now, what does our range start at? Instead of starting at 0, it starts at -3. So it'll be -3 to infinity. And what questions do we have there? Now, do you have to graph every single one of these pieces? No. I just think it's helpful to look at it visually. Most of the time, I'm at least going to graph the purple graph, because that gives me the shape of the graph that I know that I'm supposed to be moving. So if you don't graph the gray graph, that's fine. If you want to skip straight to the blue graph, that's fine, but just be careful that make sure that you are plotting correct points, because that's usually the biggest thing that I see is people just want to plug it in their calculator, which is fine, but I am still looking for those 3 key points and making sure that your asymptote is clearly labeled. Because if you just kind of have it curved off at the bottom, but I can't tell where you're trying to put your asymptote, you're not going to get full credit for that. Does that make sense? Alright, now, this is our exponential. We also have our logarithmic parent graph. Do you remember what that looks like? If you want to Not really? Okay. Well, let's remind ourselves. So, remember we talked about yesterday, exponentials and logarithms are what for each other? Inverses. So, sometimes it's helpful to think about, okay? So, if I had y equals 2 to the x, that's the one that we looked at before, okay? I'm still looking at those 3 key points, -1, 0, and 1. So 1/2, 1, and 2. The associated inverse of this would be log base 2 of x. Yes? Remember inverses? Exponentials are inverses of logarithms. So when I find inverses, remind me, what do we do? Switch our x's and y's. So from my table, I can literally make my x's go in the y column and make my y's go in the x column. So instead, we would have 1/2, 1, 2 for our x's, and -1, 0, and 1 for my y values. Yes? So looking at the graph of this, I now have 1, 0 is going to be on our x-axis, 2, 1 is here, and 1/2, -1 is here. Okay, so it is still going to increase, okay? So it is still increasing, it's just going to do so at a slower rate. Okay? Now, since I switched all of my x's and y's, we had what type of asymptote for our exponential? For our exponential. We had a horizontal. So if we switch all of our x's and y's, that means that instead of having a horizontal asymptote at 0, we're now going to have a vertical asymptote at 0. So this time my x values are going to get closer and closer to 0 instead of our y values. So what is our domain here? Yeah, so just like we switched our x's and y's, we also switched our domains and ranges. And so now our range is going to be correct. And again, just like before, we could technically make this generalized with any base. So it's going to be 1 over b -1. 1, 0 will always be the same, and then b, comma, 1. no maybe. So when you're graphing these, you kind of have two ways to think about it. If you just want to remember this pattern, you can use that for your key points. Okay. We can also think about if I have log base 3 of x, remember that the inverse of that is 3 to the x. So if it is helpful for you to first think about your associated exponential graph, sometimes that can be helpful, because then when I make my new table, again, I'm just flipping all of our points. So whichever way is more helpful for you. To first start with the exponential, or just to kind of memorize that pattern. So I have 1, 0, 3, 1, 2, 3, 1, and 1/3 negative. And again, like with our exponentials, we don't really need a whole lot of points on there, because it's going to follow that same kind of shape to where we're increasing but slowly on the right side, and we're getting closer and closer to 0 on the left side. What questions do we have? There. Alright, so then our last thing to look at is same thing with our exponentials. We have transformations with our logarithms. Still A's, H's, and K's. So stuff on the inside of the logarithm still moves it left and right. Stuff on the outside of the logarithm moves it up and down. And if it's being multiplied, that's either going to stretch or compress it or flip it if it's negative. Yes, nobody? So let's look at an example of that, and then we'll be done for the day. So what's my base on this one? You can't see it very well, but it's a 10. Okay. Did I have to write that 10 there? No, remember from yesterday that technically if I just had log of x plus 1, that's the same thing, because 10 is our common base. But we're here, they wrote it down for us. So remember that our parent function is going to be log base 10 of x. So it's going to look something like that. Yes. And then what is that 3 on the outside going to do? Stretch it. So we multiply all of our what values by 3? Nope, it's still on the outside of my logarithm, right? So it's still affecting my outputs. So we're still plugging in the same things. But then, like this first part, my log part is still going to give me -1, 0, and 1. But then we would multiply it by 3. So we get -3, still 0, and 3. So this point doesn't change. But now this is 1, 2, 3. So it does make it a little bit bigger. Then the last thing we need to think about is that +1. Where is that +1 located? How do I know it's the outside? There's no parentheses. So what's going to happen to each of my points? They're going to move up 1. And so that would be our final.